All righty. So this talk's going to be different than, I know all the talks are a little different. Try to tie in, been listening to talks over the last 2 days and trying to figure out what people are talking about, try to tie them all together. Closing something up is always interesting. You're always aiming at something and often miss. My life revolves around data analysis and telemetry, but I'm going to talk about performance monitoring. We're going to have octopuses in this, and we're going to dispose of dead bodies, and we're going to talk about time. All three things are, at some point, a systems engineer's worst nightmare. So a long time ago, I think about 6 years ago, Brian Cantrell keynoted, and I believe that's where he started talking about the octopus. There was an aquarium somewhere, and they had sharks in the aquarium, and they would come in, and like the shark was dead in the aquarium. And they're like, what's going on? It's sick? What's happening? What happened here? Right? So they're trying to figure out what happened to the shark, because they're at the top of the food chain, right? There's no predators of the shark in an aquarium. And what they found out was that this fucking octopus just like came out of nowhere and killed the shark. Like unprovoked, out of the deep, just reaches up and grabs you like a compiler bug or a kernel panic, right? You're just going along and you're the apex predator on the system. And then suddenly, like out of fucking nowhere, this tentacled thing reaches up and wastes your entire day, right? And I'm sure everybody's been in that position where they've been absolutely screwed by every component of their system. Oftentimes, that actually is time. And then, some things are not created equal, so we end up disposing of a lot of dead bodies in our occupation. So, generally speaking, performance actually matters a lot to systems engineers, but it doesn't seem to become relevant to businesses until you actually start screwing your users, which is unfortunate. I'm going to try to bring us back into this realm of we can be better on systems. But every single individual matters, right? So when they're going and using your API or they're going and using your website, it turns out if you make their experience shitty, they aren't your customer anymore. Unless you have a monopoly, like Pepco or BGE. Woo, good thing we have power today. So what does that look like? So I've found that we have made this enormous struggle in our industry to monitor the performance of systems, and we've been looking at averages, and the whole industry has been saying, hey, that's not how you calculate service level agreements, that's not how you set objectives, you need to use percentiles. And I feel like we've dragged our industry forward into this new world that's actually completely wrong as well. So, and I kind of come to that realization this year when we were doing analysis on all of our data, and we were, setting our SLOs, or service level objectives, around 99 or 99.9th percentile. And I realized that I looked at this graph and I asked some questions of myself that maybe you can answer. We'll think about it. This red line is at 1,500 milliseconds. It's at 1.5 seconds. All right, and the purple graph is the 99th percentile of all requests served at any given point of time, right? So each one of these things is probably 2 minutes or something, each little line in the line graph. So over that 2 minutes, however many users showed up, all of their latencies were rank ordered, and we took the 95th percent. So we'll get into 99th percent. So I'll get into an explanation of what 99th percentile is, but I want you to think about this at 2 p.m. here, or at 6 p.m. here, or any of these areas, where the line is below, where you are winning. What's above the line? Right, the line is the 99th percentile. There's something below the line. There's something above the line. What's above the line? And in that horrific nightmare of your 3 a.m. outage, I believe that's 3 a.m., that's right? Yeah, that's 3 a.m. Everybody loves a 3 a.m. outage, right? Who likes a 3 a.m. outage? Yeah, yes. That line's off the charts, so you obviously screwed the pooch. What's below the line? Turns out those answers are really shitty. in that they're non-conclusive at all. So what is a 99th percentile? The pro hat tip to Fred Moyer, who did the lightning talk about percentiles. I spend all day looking at graphs. This, amazingly, so anytime someone says, yeah, I know the 99th percentile, or I know the median, or I know the 25th percentile of my latencies, when we write data into our time series database at 300-minute rollups, this is the latency distribution of that. If anybody can make sense of that or guess that the curve looked like that, then you win an elephant. I mean, that's just not possible to reason about with a couple of different numbers. So we actually track every single latency of every single op. And then we build a distribution out of it. And the interesting part is that looks really good, right? I don't know if you can see it at the bottom, but like all that interesting stuff, that's less than 100 microseconds. So that's pretty decent for a database operation. It turns out that the 99th percentile is 147 mics. That's great, certainly not noticeable to a user. Very disturbing, the Q1, or the 100th percentile, the max, is 63 milliseconds. That's not an order of magnitude or two, but 3 orders of magnitude slower than our 99th percentile. Fuck, right? That's bad. Okay, so what does the 99th percentile really mean? And this is kind of an important concept. It means that at that little magical point out of 149 microseconds, everything better than that constitutes 99% of the population. Everything worse than that is 1% of the population. What it doesn't tell you at all is how bad it really is, right? So it's really important to know that. Occupy. You ever think the 99% are the ones that are having it good? Because that's the way it is in our environment, right? So this is the 99% of your users living the high life. It's great. The 1%, though, I have a question. What's it like for them? So there's sort of 3 options. Like one is that it's like dark and gloomy and shitty. Another is that they died of cholera. And the other is that they had a child eaten by a dragon, right? So it could be really, really bad. And we just don't know because we don't care, presumably, right? If you're tracking 99% and you're not tracking the max and all of the ranges in between, you just don't care. And that's okay unless you attend this conference, when you're supposed to care. So the other thing that's fundamentally broken about the 99th percentile is actually how bad the lack of knowledge affects you. So this is the same, the purple is the same graph. Now we have a little black line on here that tells us the number of users. And there's a little circle. You can sort of see a hairline up in there. It's hard to see from a distance. But there's a little hairline where we're looking at the graph. And it says that at that point, the 99th percentile is 1,266 milliseconds. Better than our SLA objective. Great. Okay. There are 860 users using the site right now during that window. So that meant that we took 860 latencies, we sorted them, we looked 95% of the way through that list, and that was 1.266 seconds. Quick, what's 1% of 860? 8.6, round to 9. There are 9 users that had a worse experience than 1.266 seconds. Did they have 1.3 seconds? Because then we totally win, right? They're all better. Did they have 90 seconds, right? Did we just Trojan their box and screw them? Like, how bad was their experience with us? And we don't know that. And a lot of times we're looking at this service level objective, and this may not look obvious at all in this curve, but you know what 99% of a really, really, really big number is versus 99% of a really, really small number is? Turns out they're really different. You know what an outage looks like at night when no one's on your site anyway? It's called no collateral damage at all, right? So the fact that during our outage at 3 a.m., we had a relatively low volume of users means that, sure, we screwed definitely 1%. We actually don't have any idea how many percent we screwed. Every single person could have been above that line. Or exactly 1% could have been above the line, and magic gap could have been there, and all the rest 99 could have been fast. We just don't know. But whatever that problem was, it actually only affected the users that were there, obviously. Now we have these little 2 brief service violations. They're 2 minutes each, not a big deal. But we did have the highest volume of users on the site around that time. So that's sort of a problem, generally. So the biggest problem is that percentages don't represent people, right? Which 1% of your users do you want to screw, right? I should probably use a different vernacular for that. Disappoint greatly. So what you can do, though, instead, I mean, you're already counting all of these things. Why don't we actually look at this around our service level objective, right? Our service level objective is not to serve 99% of them faster than 1.5 seconds. Our objective is to serve all of them faster than 1.5 seconds and realize how we didn't do our job. So what we're actually looking for is the number of users that are actually having a bad experience. It's not how fast were we for some arbitrary 99th percent or 99.9th percent or 95th percent or 50th percent. That doesn't matter because it treats all the other users above that like crap. We actually want to look at all of them and figure out, okay, what percentage of users right now are getting service that isn't up to snuff? So this graph is actually the percentage of users that aren't getting what they want. So clearly we do have a kind of a bad outage. But again, percentages of users, how do you get users from percentages of users? You take total and you multiply them together. So if you multiply the second 2 curves, you actually get the bottom one. And this is the number of users in every, this is 2 minutes, but every 2-minute interval that we screwed, right? Every time we have area under that little red curve on the bottom, we lose customers. So what this looks like is what we're normally navigating to. This is actually the cumulative distribution of screwed users, right? This outage was clearly nasty. The other stuff where we actually thought we did okay screwed exactly the same number of users. We lost the same number of users over the course of the day due to poor performance that we lost during our outage at night. And that's completely non-obvious if we're not using the data the correct way. So we need to be looking at this data the right way. And there's a technical term for this that's probably not mathematical, but quantiles are basically taking a percentage of a population. So we call this inverse quantiles. So instead of calculating the performance at 99%, we calculate the percentage at the performance level. So instead of saying Q of 99, we say inverse Q of 1.5 seconds, and that gives us a percentage. So this is how you should be looking at your data. And this is great, so it's all awesome. This is thousands and thousands, this is hundreds of thousands of data points. Well, it turns out that computers are fast, and you can take 100,000 measurements, and you can sort them, and you can figure out the 95th percentile. And this is really useful for understanding how users perceive your service. So what if I told you it's okay to care about your systems the same way? That's what I want to see, right? So great, a user shows up to your site and loads a web page, and you want to know how fast it is. That is actually more important than what I'm about to talk about. But when I do an insert into a database, or do a delete, or do an update, do a query, and that takes a certain amount of time, there is a consumer for that too, and we can monitor all of that in the same way. So now, I'm going to leave the realm of how you would do math and why you should use histograms to do things into it's really hard to do that, and there's a reason for it. So systems are fast. Users are really, really slow. So how many people here serve users on the web? How many people here serve each user in less than a microsecond? Nobody. Right? Probably nobody. I assume nobody. I want to be on your drugs. That'd be fantastic. So the problem is that systems work at a speed and a velocity of processing that makes it much more difficult to measure because the quantity of measurements is high. So what happens is, in a website, when important op is serving your web page and it's 400 milliseconds or 200 milliseconds or 30 milliseconds, you figure out what time it is, you do your work, you figure out what your time is, you subtract the two, and you log it. That sounds awesome, right? That's how I assume everyone does it, because there's really not another way. Well, it turns out that when that important op starts to converge towards 0, the time it takes to figure out what time it is twice and subtract them and record it becomes significant. So when you're doing this in a database and you want to track the latency of every write to every spindle or every write to the database, and the database operations take a microsecond. Anybody here have a database that can write something in a microsecond? Probably do. Most of them actually can do that. Usually it's in a batch, right? You open a transaction, you write 10,000 records, and you close it. And when you divide that out, those individual operations didn't take that long. But how many people here have a database that can write something in 100 mics? Yeah, 0.1 milliseconds, not uncommon at all. So, I mean, that's only 10,000 transactions a second, 10,000 writes a second. That's not much. So what we found while we were trying to do this, trying to use our own tools to analyze our own stuff, was that we couldn't. And the reason is because, we'll get super technical here, getting HR time. So this is getting a nanosecond resolution timer on a box. Okay, we run everything on a Lumos. And you can say, why do you do that? That's a horrible idea. Because it turns out it takes 300 nanoseconds to get what time it is to the nanosecond. So if I call it in a tight loop, I can only do it every 300 nanoseconds. So Linux is 120 nanoseconds. And you would say, why don't you just use Linux? It'd be 120 nanoseconds. Turns out after I write my 10, 20 terabytes of data, I can't read it back anymore because there's no good file systems on Linux. So there's a problem. So we use that, and we want to make it faster. There's good news if you use Linux. You can actually use what we did. So we have this problem that our important op is 1 microsecond, all right? And getting what time it is 300 microseconds. Getting what time it is again is 300 microseconds. And logging it can be incredibly expensive too. So it's already a minimum of 60% overhead load. The probe effect is 60% on just doing the operation. Okay, that's an enormous probe effect. In fact, it's so enormous that you can't afford to do it when you're doing performance profiling. Anybody here run a debugger that shows? Anybody here run New Relic APM? Anybody? You run it on every request, right? Anybody run it? No. Of course you don't. Why? Because it's slow as shit. It's super valuable, fantastic tool, right? It's really, really useful, gives you great insight, but it's so much probe effect, it slows down the app so much that you just can't run it on every request. Well, if you want to track the distribution of the entire behavior of your system, sampling becomes an incredibly difficult problem, so we don't want to sample very often. We want to sample always, right? 100% sampling rate. So the question is how do you make time go faster? So the first thing is when you probe something, there are 3 main keys to probing something. The first thing is that you should always have order 1 operations. There should be no data structures that have any sort of log in squared, anything like that. Everything should be a fixed size. It should not depend on the capacity of the system, the size of the request, or anything like that. You should never have any latency bubbles. So if you expect it to take 30 nanoseconds to log something out or 30 nanoseconds to calculate something, it's really fucking inconvenient when it takes 90. Because then suddenly all of your plans go down the drains. So, and then the obvious thing for that is that you should never be allocating memory, because that always has magically horrible things happen when you allocate memory. So, time. So how do you solve the first problem? So I don't have detailed slides on this, but I'm going to say that we solved it. There's a GitHub link to the repo that has the code in it that solve it. And all of the code is in a file called mtev_time.c. But what we did is, so all modern processors, starting with Sandy Bridge, which is like 2011, 2012 Intel, they have this thing called a TSC. It's a timestamp counter. Basically, it ticks with the CPU. It's like tick, 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 tick. Okay? It does that, depending on the CPU, somewhere between 2.5 and 3.6 times every nanosecond. worst thing that anyone ever did in the processor world is enable power saving mode on processors, right? So power saving mode isn't so bad, but what they thought was, what we'll do is slow it down, okay? How often is that so cool on your stopwatch when it's like, I'm just gonna slow down for a little while, I'll speed back up later when you have something to do. It's like, it's really hard to tell time that way. So in 2011, 2012, sometime around there, they introduced a feature in Intel chipsets called invariant TSC. And what that is they said, yeah, we'll go into power saving modes, we'll slow things down, except the tick. The tick will keep going at 3.6 times per nanosecond, or what have you. So that's fantastic. That means that if we can get at the tick counter in the processor, and we can measure how fast it's going, then we can figure out how much time has elapsed. All right, so then there's another problem. So how many people here have a processor in their machine? It's a trick. You probably have processors in your machine. And they all have different idea about what time it is. Significantly sometimes, like sometimes 30 seconds different idea of time, which is a really bad problem if you're trying to measure nanoseconds. So what happens is each core on each socket, and it depends on which revision of processor you have. Sometimes all of the cores on a single package will be that way, but definitely different sockets. As they get booted by the operating system and online, their idea of the beginning of time starts. They're all online at different times. And guess what? When you check what time it is, and you get your counter, and then you check what time it is again, you might not be on the same CPU. So when you ask for the counters, you get two completely great counters that are relative to points in time in the past that are arbitrary and unequal, which is useless. So what you can do there is that you start up and you start calibration loops on each core, and you bind them to the core, and you figure out how fast the cores are running, and you figure out how much they are offset from time, real time. And then you can basically, it's really awesome, it's y equals mx plus b. Does anybody remember that? Come on, yes. All right, so I mean, I have 3 daughters. One's in 8th grade, 6th grade, and 4th grade. And y equals mx plus b, I can say it to any of them, and they're like, oh. So fantastic. So m is your tick count. It's 3.6 times, or 2.955, or whatever it is on your processor, depending on your processor speed. So if I basically run in a really tight loop for a couple seconds, I can figure out how many ticks happen in a certain number of nanoseconds. So what we do is we trust the system. The really slow 300 nanoseconds get time of day, get HR time. We run that and figure out how many ticks are there. Then we wait about 5 to 30 seconds, and then we run it again. Okay? So now we have 2 points on a line, and we can figure out the slope. It's fantastic. Now we have the ticks per nano, right? And then what we do is we figure out what time it is on that core, and we figure out where the y-intercept is, which is fantastic. Okay, so now we have m and we have b. And the ticks is x. Actually, the ticks is y. You have to solve backwards. But all you have to do is get the timestamp counter off of the CPU, figure out your m and your b for that core ID, and you multiply, and you're done. So this should have been really easy. There was a lot of confusion as to what was going wrong. One of the things was, it turns out that m is a double, and b is an unsigned 64-bit int. And when you write them out, you should notice that boom, boom. A lot can happen between boom and boom. So if I write one, and then go to write the other one, but someone reads them and then calculates y equals mx plus b, those are really, really big numbers, and if one of them is adjusted, they're a pair. So when I write the two of them together, if I don't write 16 bytes at a time, then I can interleave and occasionally, be ticking along with like a 2 nanosecond variance, and then it's like 17,000 milliseconds off. And then boom, it's right back on. And it's because those 2 8-byte writes weren't happening atomically. So that took a little while to figure out that that was happening. So there ends up being 2 chipset features that you absolutely need. Both of them came with Sandy Bridge, thankfully. One of them is CX16 CPU bit, which allows you to compare and exchange 16 bytes at one time. And the other one is invariant TSC. So with that, what we do is we have, for every core on your box, a cache-aligned size buffer, and we store 16 bytes in there, and some other accounting information to make things nice. And then when you want to know what time it is, you use the RDTSCP call in Intel, which says, read my timestamp counter, and by the way, hand me my processor ID back with it. So I read the timestamp counter, I've got my processor ID, I know which one of those to look out, I pull out M and B, I do math, and I give you the nanosecond times. So what did this do? And it turns out it's really interesting, and this is kind of the purpose of this talk and that we can do better. You figure that Linux and FreeBSD and even Sonos and Solaris and Illumos, telling time's pretty frickin' important. So somebody invested a lot in making sure this fast. How much performance improvement can you really get? 5% would be awesome. Fantastic if I get 5%, maybe 10%. So like I said, 300 nanoseconds for Illumos, 120 nanoseconds for Linux, flat 40 nanoseconds all the time for this. That is something to write home about, right? So now, instead of a 300 nanosecond measurement, bracketing that, which is a total of 600 nanoseconds, it's now 80 nanoseconds. That's all open source. I've handed it to the team that does some time stuff inside of FreeBSD, so I assume that'll go back in the FreeBSD kernel probably quickly. Linux, there will be some sort of sacrificed chicken to get it in, and an argument, of course, an argument on whether it should belong in libc or the kernel, or I don't know how that works. You know how always people say you take open source and you just can't dump it over the fence? There are certain communities where you really appreciate the fence being there. And you can just dump it over and you can walk away and just hope for the best. That's maybe one of those communities. So the other thing that we did was the logging of that. And as you'd imagine, that logging something can be pretty expensive at times. So we also just open sourced libcircmetrics, which actually is written by Circonis, but doesn't actually need Circonis product to use it. It's a C library that allows you to track metrics inside of any app in C and any app that can bind into C. And what it does is it leverages log linear histograms to track that sort of thing. So you can say, oh, I'm going to time this database operation. It took 932 nanos. Log the fact that it had 932 nanos. So obviously, to remember that, you also don't want that to take a lot of time. So the features of that is it tracks counters and gauges and things like that, but it also supports histograms, and they fan out over CPUs. So as you're using them, they end up being lock-free as well. So you can go in and log at a flat 10 nanoseconds, that stuff. So no allocations or anything like that. So that actually drops our observational time from before it was like 640 nanoseconds, which ends up being a 64% load on a 1 microsecond transaction, to 80 nanoseconds flat, which is 8%. That was about a week's worth of work and using a napkin, right? You use a napkin and you're like, this is how fast, 300 nanoseconds. And you think, well, how do computers tell time? You work through it and you're like, that's like an order of magnitude off. That has to be horrible. And then you pursue it out of curiosity, right? Why is this shit so broken, right? And everybody here has used a piece of software in the last 24 hours that they've asked themselves, why is this shit so broken? Probably I've used my own software. So I think the interesting part is that, and it's easy to get lost in this sometimes, and to pursue things that don't have much gains. But a lot of us sit on the outside, and I see this a lot in the industry, where a lot of us sit on the outside and marvel at that fucking octopus that can kill you through safety glass, okay? And that's okay, I guess, but not if you come to this conference. This conference is for people who do things. They fix things. They tackle really hard problems, all right? So my one ask for all of you is that you go be curious about why your systems don't work correctly, get in there, and actually take some risks, right? Like cope with having that bad day with the octopus. And that's it. Fight the octopus. Anybody have any questions? There's one.
Whatever the impact of the pipeline flush and this RG flush on your ad performance?
The pipeline flush from the
RDTSCP,
comp exchange?
No, our DDSCP forces a pipeline flush
It
because of its half barrier semantics, right?
as opposed to without the P. I mean, you have to get the tick somehow.
Yeah.
So
So you're just saying it's 8%, but that's a micro benchmark kind of workload, right? So I'm asking about the wider effect of monitoring if you use RDTSCP.
So I guess we haven't had a good way to measure that comprehensively. Usually the stuff that we're doing is we're not tracking things that are nanoseconds long, right? So we're usually going across function boundaries. We've kind of probably already screwed our pipeline on our processor completely in that important op. So we've done bad things already there, right? It's a microsecond long, and a ton of stuff has happened in a microsecond. We've probably been through a long call chain of functions at that point. So I don't expect it to be enormous, but it would be if you were doing something like a tight loop where you were trying to measure something really, really hot. If you were doing benchmarking on like computational processing or something like that, then I would expect that might be a little painful. I'm not sure there's a way around it, though. I mean,
We can talk about it later.
yeah. All right. Bye.